Thanks everybody for coming. My name is Charles Ging. I'll be talking about the project, an open source project that I recently worked on with 2 other developers called RedPoint. It's a web-native computational notebook geared towards programmers. And in this talk, I'll kind of briefly give you an overview of the kind of high-level goals and features of this notebook. And then we'll dive into kind of the technical journey that we faced. So first of all, what's RedPoint? It's this computational notebook optimized for note sharing and sharing notes about code or algorithms with your fellow developer. It allows you to write and execute, at this point, 3 different programming languages within the same browser. So currently we support Ruby, JavaScript, and Python. And interleaved,
Up to you, if you're going to sit down.
That's all right. And then interleaved with your code cells, you can also edit markdown cells that can be rendered between your runnable code. And as a web native app, we're able to leverage some cool technologies that I'll describe later. So let's take a step back. Is there anybody familiar with computational notebooks, Jupyter notebooks? So we're, okay, not a whole lot. So I'll just kind of give you the quick and dirty, very quick and dirty. There's this notion of a cell-based design where you have multiple cells. In this notebook, we have 3 JavaScript cells, and then we've got some markdown in between them. And then all of your code cells share state. Yeah. So then you have descriptive cells, not part of the code, that you can use to document code or describe algorithms or present questions about a snippet that you can share with someone. And then the combination of runnable code cells and then this rich markdown text allows you to create these computational narratives, right? So it's an interactive document that you can share with others who can receive your code and your questions and then iterate on what you've written. So most of us may have our go-to note-taking applications, which are static documents, right? So on the left, we have a Quiver notebook, where we have markdown text, and then static code. So there's some overhead involved in copy-pasting your code right into your editor and executing it. And then here, I don't know if anyone's familiar with Observable, HP. It's very awesome for data visualization. However, it has some unique flavor of JavaScript that requires a little bit of just a bit of a learning curve before you can use it. But it's a very cool tool. You can adjust these sliders that adjust inputs to the code below and then affect that visualization. So we wanted to pin ourselves somewhere between static note-taking apps and then these computational notebooks that are very popular in data science. So very awesome tools. However, there are some kind of gotchas regarding hidden state and kind of a complex hidden state and scope. Not very user-friendly, especially for new programmers or people learning a new language. So, and then like I mentioned with Observable, some of them have kind of a unique flavor of the supported language. So why did we build RedPoint? Again, I said it was to fit somewhere in between these static notebooks and then a rich data science geared notebook. So yeah, and then this project is free and open source, so it's relatively easily self-hosted. There is some configuration involved. But so in today's talk, I'll just give you an overview of our goals, some of the core features, some nice GIFs. Then we'll talk about kind of the foundations of the project, the network architecture. User experience really drove how we execute code and then render the results of that code execution cleanly in the UI. And then we'll talk about security concerns, because we'll get to that, but then also management of our host resources among concurrent sessions. And then lastly, I'll give you just the overview of the whole system architecture. So then the high-level goals are to provide a predictable scope and state. I kind of alluded to some of the hidden state that you see with existing notebooks. So we want just a top-down state and scope, as if each cell of JavaScript on this notebook belongs to the same script, right? We would like to clearly display the results of code execution. So here we just have some log statements in there highlighted in green. We'd like to be able to execute multiple languages in the same notebook. They don't share the same state between different languages. That would be cool, but each set of languages belong to one another. Right? And then we wanted to leverage the web native status. Again, I'll get to some of those features we were able to enjoy. So here's that first goal. As a multi-language notebook, we can add a Ruby cell, there's a JavaScript cell, and then last we'll add a Python cell. You could either run one of these individually, or at the very top, you can run them all. So it's very nice to compare language features across all different languages. As a web app, we support ingesting both API data and webhook data, so I'll get to that a little bit later. And when you receive that data, you can then add a cell, another JavaScript cell, and then interact programmatically with that payload. And again, it's free and open source, so list it as you wish. So first, we'll talk about some network architecture and the early decisions and challenges we face. So step one, we're allowing the user to edit and execute code. Where are we going to execute that code, right? So you can do that on the client side or on the server side. And on the client side, of course, the major benefit is that your browser interprets your code. Everything's super speedy and fast. There's no latency, right? So then the downside of the client side code execution are that we have no control over the resources powering a user's session. So we'd like to provide a uniform experience for mobile users as well as desktop. And the biggest downside to a client-side execution is that browsers only support JavaScript. So unless we provide an in-browser compiler for every single supported language, which would create a very heavy client-side app, we're limited to JavaScript. Right? So we chose to execute code on the server side, which allows us to manage and include support for multiple languages a bit easier just by including that language's runtime on the server. We have consistent resources that are within our control, so it allows us to scale a little easier. And the downside is the latency incurred by that round-trip visit to a server and back, right? Of course. And then, of course, we're allowing people to run arbitrary code on our system, so security is a big issue. So we took a few steps to mitigate that, which I'll get to a bit later. But now that we know our server's running our code, we needed to decide on a protocol. How are we exchanging this data, right? So early on, in our early prototypes, we just said, let's just try it out over HTTP, which worked well in very simple code examples. But since our server can only issue a single response per request, things got a little, the experience left a lot to be desired when given some asynchronous code or code that executes at different speeds, right? So in this example, you see we have a set timeout in the log statement and then a console log high. That high won't be able to be rendered until we finish executing the code, which will be in 10 seconds, right? So we're going to only be able to render everything all at once. So we need some sort of a persistent connection, or persistent-like. So we didn't really, we only very briefly considered the idea of polling, which would be wildly inefficient to submit some code for execution and then rapidly pull that server for its standard out in return. So we quickly ditched that idea. Server-side events do offer a persistent connection, but it's primarily a one-directional flow where a client subscribes to some data stream. So we needed a two-way street, right? So WebSockets offer us a fully duplex form of communication, which would allow our client to submit code to the server for execution. During the process of executing that code, we can fire back one or many WebSocket messages in response. Another advantage to WebSockets is we can easily detect a client's disconnection when that close event fires, allowing us to free up resources associated with that user's session. And there's decreased latency, as each WebSocket message has a much smaller packet size than an HTTP request. And then just the primary trade-off with WebSockets was some added code complexity, namely in proxying, which I'll get to in a bit. So that same asynchronous code now will look like this over a WebSocket connection. After that initial HTTP handshake, we get that fully duplex connection, and our user sends some code over to be executed, and we generate a script and run it as a child process, and are able to listen to the standard out. And when we get standard out off that process, we just fire back WebSocket messages to the client, and then receives it, renders it in the appropriate spot. So now let's talk about our user experience, because as I said earlier, it really dictated how we execute our code. So our design goals for the user's experience were to, again, provide that predictable top-to-bottom scope and state. I mention that because it sounds like there aren't too many people familiar with computational notebooks, but it is possible to run cells in arbitrary order, so you can jump around the page. So we wanted a top-down scope and state. A clean user interface where we render results under the cell responsible for that piece of feedback off that code's execution. So the first question is, how do we share scope across multiple cells of a given language? And it's a fairly straightforward approach. Say we have a notebook with 3 Ruby cells, and third cell is executed, which is effectively the same thing as running all Ruby cells or all cells of the same language up to and including the cell you've run. So when the user runs the third cell, we send the code cells over in an array, which is received by the server, and it's joined together into a single script, so that variables declared in the second cell are in scope in the third. So then how do we get these clean execution results without too much hassle? So you'll see our output is highlighted in green, so return value will come out in white, and errors in red. So our options are to generate a REPL process for the appropriate language type, and feed the user's code into that REPL, and then parse the results. So that's one option. And then the other is to generate a temporary file of the appropriate language, so a JS file or RB file, whatever it is, and execute that, and see if there may be an opportunity to get these results of execution a little cleaner than parsing. So I've kind of alluded to this a few times, this notion of hidden state, and it looks like this. And this is by no means meant to bash on these existing solutions. They exist for super heavy data, basically huge data sets, where you're able to minimize or save the computation of an earlier cell. What that would look like for us in a fairly simpler approach is if you declare this variable and execute it, this cell, only to realize in this const declaration we have a typo, and we come over and in the same cell we fix the typo and execute that once more. We get this error that the variable's already been declared. And that's because there's a persistent REPL that powers this notebook. So across all execution requests, there's a persistent REPL running in the background. So we've had 2 const declarations that we can't see. So this is a pretty simple example, but you can see how much more complicated notebook that could drive you crazy, really. Unless you're used to those notebooks out there, like Jupyter, they're great. So what we chose to do instead of this having a persistent REPL is to respawn a REPL process for every code execution request. So instead of stacking state in a REPL that we can't see, we just spin up a new REPL every time. So it's kind of what you see is what you get. That code top to bottom is thrown into the REPL as you see it in your notebook. The trade-off here is that unlike Jupyter, we have to perform computation on every cell. They're able to save the results of an earlier cell's computation, which is very handy when you're dealing with massive data sets, but we have a slightly different use case. So if we relied solely on a REPL to parse out results, we'd fairly easily be able to parse the last line of the REPL, right, to get that return value. But to get errors and logged output, we'd be tasked with coming up with a pretty complex parsing strategy. and a parsing strategy per supported language to skim out all the version numbers and everything else you see. Additionally, errors aren't going to halt the execution in a REPL. We're just going to encounter that error and then feed the next line into the REPL and again. So not great, but fairly easy to parse the return value. The other option is to build a temporary file, like I mentioned, and execute that as a child process, and listen to data events on standard out and standard error. And so in this little image, you can see that happening during the process. We get the standard out, fire it across to the client. We do the same with standard error. Standard errors will also kill the script's execution. So if you encounter an error in the second of 3 code cells, you're not going to see anything of that third cell. So we're easily able to get standard error, standard out errors, errors halt execution without any weird complex parsing strategies, so that's great. Then the drawback is we don't have any return values. So we implemented a combination of these two strategies using the promise chain, where we receive the code, generate a script, execute that script to obtain standard out and standard error, fire it back to the client. If there are no errors, we then execute the REPL, parse the return value, fire it back to the client. If we do encounter an error when the script executes, we just reject that promise, exit the chain. So then, where do we render the results of code execution? Since our script that we build on the server, that's an aggregate of all the code cells, has no notion of a cell-based origin. Right? So that looks kind of like this. Our code cells come over to the server, they're joined into a single script. We listen to the standard out, fire messages back to our client, and it goes, where do you render me? How do you do it? So our approach was to use the delimiter strategy. So when we received codes, a bundle of code cells and generate that one script of them, we inject these log statements or print statements that contain a UUID. So that way, when we're listening to the standard out of that script, when we encounter one of these delimiters, instead of sending the value over to the client of that delimiter, we just send a message that says, hey, React client, increment the cell that you're going to be rendering below. So it's kind of a little delimiter strategy. So let's get on to security and resource management, because obviously when you're allowing people to run their code on your server, it's kind of a scary situation. We also need to be able to manage our host resources across concurrent sessions. So major inherent concerns are a malicious user interfering with your host file system, deleting files, escalating the privileges, gaining control of everything. Sky's the limit, right? So there's a lot to be considered there. And then another concern we had was spreading the host resources evenly across our users' concurrent sessions. So the first question is, how do we safely execute some users' code? A naive approach would be to just, on the client side, just come up with a blacklisting strategy, parse their input, and reject any requests that contain something that looks scary or harmful, right? So that's possible, I suppose, but you'd have to be very creative and comprehensive in your parsing strategy to consider every possible malicious attempt that could be made on your host system. Not only that, complexity in your application logic, you could misidentify some non-malicious code, rejecting somebody's friendly code, leaving them with a poor taste in their mouth. So the approach we ended up taking to isolate user sessions from one another was more of a system-level approach, where we containerize each session in a Docker container. And by spinning up a separate Docker container for each session, we're able to effectively provide some layer of isolation between sessions and a session and host. Let's see, so very brief overview of Docker containers. Each of these containerized applications is built based on a Docker image. It's like a blueprint for your application, contains all the software and dependencies that you might require in this virtualized operating system. They're very fast to spin up, which is handy since we're providing one for every session. And yeah, and using that blueprint, we can just spin up as many as we like. Also, we can deploy our application on any host system, regardless of its configuration. So, containers. So using containers to isolate our user sessions, if a user enters some malicious code, they are only impacting their copy of the application code, leaving other users' sessions unharmed. Also, each user has a fresh copy of the application, so there won't be any remnants or artifacts of previous sessions. So another step we took to protect our Docker container was to create a new non-root user, and this is because by default, in a Docker container, the default user is granted root level permissions, which afford that root level a few too many potentially harmful commands. So in our Docker image, we define a new non-root user, give that user a new bin folder with safe whitelisted commands, and then in order to keep that user from potentially changing their bash profile to gain access to other binaries, we changed the ownership of the default user's bash to root, and we revoke their write permissions in their own bash profile. So with those layers of security, we still could benefit from another layer of insulation from the host. So we implemented, so Docker containers aren't a true sandbox. They have direct access to the host's kernel. And I mentioned they spin up very quickly, and it's for that reason. They interact directly with our host kernel. So if our malicious user happens to be able to break from their container despite the previous safeguards we've implemented, they have direct access to the host kernel and perform a kernel exploit and escalate their privileges and gain control of everything. So that's to be avoided. So we implement a technology from Google called gvisor, which provides a much stronger isolation between a container and the host. gvisor is an alternate secure runtime for Docker containers. It re-implements system calls in a safe rule-based way. So it basically is bodyguard for system calls to your host kernel. It also virtualizes the host's file system, which means that, again, if that malicious user starts messing with the file system, they're working on a virtualized copy of it. So this sandboxing wasn't without some trade-offs, because as an alternate runtime, gvisor consumes a bit more memory. So we could support after some load testing, we found about 25% fewer containers on our host. And then there's also a slight hit performance in each notebook, but given the increased security profile, we're okay with these trade-offs. So how do we now prevent one container or session from hogging the host's resources? So in this little slide, you see a greedy container running some infinite loop, right? And this container is going to hog our host resources, and that's because Docker containers will consume as many CPU cycles as possible unless we govern it in some way. So in this example, without any strategy of spreading those resources out, this user is going to be left, they're not going to be able to, what's hello world? Console log hello world. So we need some strategy of spreading out those resources. So we do that with Linux control groups. And one of our Docker configurations, when we spin up a new container, allows us to govern or set a limit to how many CPU cycles a container is allowed access to. So in setting this, we're able to provide a performant application, but we also prevent any one user from just taking over our entire host's CPU. All right, so now that we've talked about security, let's look at our system architecture, maybe what we've all been waiting for. So now that we're containerizing our applications, we've addressed our security concerns, but we are left with some interesting engineering challenges. How do we connect a user to a container? How do we manage that user's session data? And how do we handle our persistence, since we support saving, cloning, and of course loading a notebook? So our solution was for managing all these interactions was to build a central hub we call the dispatch server, which has three primary responsibilities that I'll talk about, cover briefly in this section. So it stands up as a reverse proxy. It manages our session data and container management, so it spins up trace on containers. And it also centralizes database interactions. So here's the overview of the system. So over there, we have our React client on the front end who does all of its communicating with the dispatch server. That dispatch server speaks with Redis, where we store our session data and where we queue webhook data. I'll get to that a little bit. The dispatch server also talks to MongoDB to persist notebook data and webhook data associated with the notebook. And then it also lastly stands between client and that client's containerized application, and it proxies messages and requests between the two. So now that we're connecting users with containers, we need a strategy of mapping that user to their container, right? So the native solution is to port forward and assign a port on our domain for each user session. It's a pretty straightforward approach and an easy mapping to map that unique port to that user's container, but it's pretty vulnerable to a port scanning attack, where a malicious user or bot could just run through a bunch of ports, gain access to a live session, and there goes that session security, right? So our dispatch server masks the internals, masks the location of these containers by acting as a reverse proxy. So we receive all our messages from the client by way of the dispatch server, who recognizes the session and maps the messages to the appropriate container. So that looks something like this. If anybody's not familiar with reverse proxying, well, our client sends a request to the dispatch server, so that they send their code to be evaluated to the dispatch server, who does a lookup for which container to send the request to, sends a request along to the containerized application server, where we execute the code and then fire back WebSocket messages to the dispatch server, who forwards them back to the client where they are rendered. So then the next responsibility of that dispatch server is to manage Redis, manage session data in Redis, and spin up Docker containers for a new session, as well as tear them down when that session is terminated. And so since our reverse proxy hides the IP address and port of the container on our host system, and our client has no awareness of that actual IP address, we need some way to map the requests and proxy the requests back and forth. And so we do that by assigning a unique subdomain URL. That's the key in that, it's the key to that hash. And that subdomain URL is the user's URL that they use for the remainder of the session. So that URL is kind of used as a lookup key whenever messages come from the client to the dispatch server. It looks up the actual location of the container and forwards the request along. And by generating a sufficiently unique subdomain URL, we ensure a pretty good degree of security. So now that we're collecting the session data in order to proxy requests, we need to store it somewhere. And the easy approach that we started with was just storing it in a JavaScript object on our dispatch server, which was easy and straightforward, but it offered no great degree of persistence. If we need to take that server down for maintenance or if it suffers some downtime, there goes our session data. So we use Redis to persist session data a bit stronger. It's still very speedy as an in-memory key value store. And it just as a downside, increased a bit of complexity as well as configuration if you were to host this on your own. So finally, the dispatch server centralizes all our database interactions. So we prohibit clients from interacting directly with our database. So all queries pass through the dispatch server before any data is persisted in Mongo. And the coolest thing, in my mind, about the dispatch server is that it stands as a consistent endpoint for webhook data, which is just the last feature I'll talk about tonight. So, everyone or most people familiar with webhooks? So each notebook is assigned a unique endpoint. So if you choose to register that endpoint with a webbook provider, you can do so. Let's see. So webhooks are asynchronous and event-driven. So user can register their endpoint with this external service, and when an event occurs on that external service, it will post some relevant data to that unique endpoint, which is handled by our dispatch server, and we store that data away in Mongo in the associated notebook. But since we're no longer in control of the rate or the quantity of incoming data in webhooks, as opposed to APIs, you submit a GET request, you get what you asked for. Webhooks, we're not in control of that rate of traffic hitting our system. So when a webhook provider posts some data to your provided endpoint, we first put it in a buffer in a Redis message queue, where we have a background process that at a set rate dequeues that data and sticks it into the document in MongoDB associated with that notebook. Thanks for coming tonight. My name is Charles Ging. I'm looking for my next full-time opportunity. Here's a more complete write-up about the project and some of my contact info. Thanks.
Couple questions. You mentioned Jupyter. What does Jupyter not do that you wanted to do this for? Is Jupyter a similar computational framework? I don't use it. So
it's definitely geared towards data scientists and data science. We wanted something that was a bit easier just to spin up and share some executable code next to some notes potentially. And if you've ever tried to use a Jupyter notebook, there are some easier, like there's a desktop, those screenshots from an app called Interact. Just a bit easier to get started using, but yeah, I don't know if that answers you.
yeah, and then you mentioned Docker containers, but where do you live? Where are your Docker containers? I mean,
so our
host,
host,
GCP, and how do you pay for
yeah,
that?
so our entire, we chose to host on GCP. And so on our instance, we have our Docker image. And when a request comes in, we use the Docker remote API from within that application or that dispatch server to spin up a new container based on that image. So we had a continuous integration where when something was pushed to master, the image on our GCP instance is updated.
Okay, the GCPs are free, right?
Correct.
If I'm a user, how do you pay for the time on the server for those Docker containers spinning up?
We're currently paying for them.
Okay. Well, thank you.
Yeah.
All right.
And this is the write-up URL. If you want to try the application itself, it's at redpointnotebooks.com without any spaces.
I'm not super familiar with Docker. I mean, I hear about it at a lot of talks. So this might be a stupid question, but do people use Docker for security reasons a lot?
Yeah, I'm no. Yeah, I think it's a standard use case. I'm no professional with Docker containers by any means, but they do offer a bit of insulation, especially when you're talking about because it's a virtualized operating system. It does offer some a bit more difficulty to start interacting with the host and other sessions.
Can I throw something out with that? So we've done a few talks on Docker at the Java User Group, and I think it's slimmed down. It's not a full OS. And if something goes bad, just kill it. Let's get another one. They're really lightweight.
Right.
They're fast to spin up. It's not like a VM. So that's why.
Cool.
That helps.
What if you not do something more native to just be like a pops out for the messaging system?
That's a great question. I'd like to hear more about it. I don't know, we just went with Redis since we'd already used Redis to persist our session data, and there's some nice libraries for managing a message queue.
And the Redis would because also GCP has a memcache service.
Oh, it's right on GCP also.
Yeah. But are you using the service for memcache of GCP or are you using?
No, we've just installed Redis right on the instance.
Oh. We could save some money.
Okay. that's good to know.
Those are really helpful. thinking of it for like, demonstrating like, interactive documentation for the AI. That's how I use this and how basically how far can it go? Like, what's like the most complex things to run into? Can you sort of import sort of resources and essentially the documentation? But like where's the limit? What's the most crazy thing you've done?
This is about as far as we've gotten, but we have considered the possibility of including different libraries that you could use. Support just a handful of libraries. If you haven't heard of RunKit, are you all familiar with RunKit? Check that out. It apparently has every single NPM package so you can just include a package and interact with it, and test it out. Yeah, the RunKit is pretty sweet. But they don't have multiple languages.
So you only have access to like the HTTP library and requests outside of this.
Yeah, I mean, sky's the limit really as a web application. I suppose that's entirely within the realm of possibility.
Have you thought instead of running your code in your own containers, just throw it on GCP function? Like you could have this serverless, I think. Besides the sockets, you might have been able to have the serverless.
I hadn't considered that.
And you don't have to pay for it. Well, you play some.
Serverless is free.
Well,
GCP. Well, kind of.
depends on
Depends on
you can do functions
free.
and you can kill all the security issues GCP did before.
Sounds like a pull request.
That's great.
I want to say, as an individual who stares at screens for the majority of their day, I appreciate your attention to dark themes.
Yes.
You'll like using the notebook. It kind of reflects the
You should
same.
have a toggle.
There is a toggle, but it's not for the theme. It's to like remove all the runnable. It's a presentation mode.
So along the lines of like when you're saying go that hadn't occurred to you, right? When you're building a project like this, you run into a lot of things, a lot of problems that you know you need to solve, right? You're like, okay, well now we need to do this thing, right? But like specifically when you got to security and some of these other things, how did you go about educating yourself on the things that you didn't know, right? Like the Rumsfeld, like the unknown unknowns, right? Like when you get there and you're like, we need to make this more secure. Like, it's some very like concrete, good examples of this could be a problem and this is a way to go about it. How did you go about educating yourself on the right and wrong way to do that, and even what the problems were you were trying to solve to begin with?
Sure. So originally, it's just over HTTP. We had a simple application server that has there's a pseudo terminal called a library called Node PTY. And we're just interacting there, and we started issuing some system commands and realized, man, there's got to be a way to start to isolate this. And none of us had much experience with Docker containers, so part of it was just the desire to learn more about Docker, knowing that we could use that to hide security. And then we learned about the sandboxing using gvisor, which is a secure runtime that's configured on GCP. So, that's more or less the process, but I don't know if that.
No, it's okay. I was kind of curious how that discovery process went.
Yeah, so partially it was a desire to want to interact and mess around with Docker since we didn't have any experience. So,
Cool.
Yeah.
And actually, a small follow-up. How long were you guys working on this? It seems like a monumental task.
It was about 3.5 months.
That's it? Wow.
Yeah, it was pretty full time.
Oh, okay.
Yeah,
How many people?
3 of us.
Wow. Well done. I mean,
Thank you.
Would you still have used webhooks, knowing the challenges you face when you're having to webhook queues?
We had wanted to use, be able to interact and test webhook payloads from the very beginning, but left it as like a cherry on top, which ended up, it really wasn't as complex as any of us thought it would be, really. First, we implemented just a client-side API call feature where you can give an endpoint to an API, and then the React client just receives the payload and inserts it at the top of the notebook. And then it was kind of iterating on that, where we have a drop down and we say the client app provides your endpoint, and basically the dispatch server recognizes the notebook it belongs to. So there has to be a notebook that exists in order for it to receive webhook data. So if they haven't already saved, once we create a webhook endpoint, we save the notebook. And I don't know if that.
I was wondering if you would use just typical HTTP requests over webhooks.
Well, webhooks were just an additional feature just to be able to interact and test webhook data, since as a server-to-server communication, it's kind of a hard thing to start testing a webhook's payload unless you already have a system up and running. There are some solutions out there, but we thought, why not stick that in this project also?
All right, I think we got time for one more question.
I'm interested if you said you didn't like 3.5 months. What type of project management issues did you run into with only 3 of you working on this project?
It was pretty tough sometimes to decide what we wanted to really focus on, but we decided pretty early what the general MVP would look like. And these guys I worked with were awesome. Worked with fairly little, disagreement, but we had our Trello boards and met in the morning, and then we'd decide what we'd go and grind away at, and then call each other in, pair if need be. But yeah.
I think it's amazing you got 2 people to commit to something like this.
Yeah. No.
Thank you.